we're going to look at in this section is graphing some of these trigonometric functions. And they actually have really interesting graphs, especially sine and cosine. Tangents is a little wacky, but sine and cosines are really nice. Just to do that, to put it all together in a really nice way, what I'm going to do is scale all of these triangles down. So we should be able to get some good values out of them. Okay, so I've got my 45, 45, 90 triangle. First of all, it's got a 1 root 2. What I'm going to do is actually divide the whole thing by root 2 so that the hypotenuse is scaled down to 1. And if we do that, I'll just get 1 over root 2, 1 over root 2, and 1 for my sides. I should have the same angles on the inside there, 45. And I'll just do the same thing to the 30, 60, 90 triangle. So I want the hypotenuse to be 1, so I'm going to just divide everything by 2. And what that should give me is 1, a half, and root 3 over 2. And so just the reason why I'm doing that is so that I can very nicely actually draw all of these things on the XY plane. So I'll get it started. But we have a lot of angles that I'm going to be able to draw in this picture here. So for example, let's say I draw, I want that actually to be in blue. I could draw that 45 one right off the bat. So my 45 ratio. So the R value is going to be 1, but what I would actually have if I draw the point at the end would be 1 over root 2 and 1 over root 2 and an R value of 1. Let's say I draw like a 30-degree angle, so that might come in roughly about here. I'm going to have the same R value. It should go a little bit higher, I think. Yeah, so same R value. And then if I were to draw that point, my X is root 3 over 2 and my Y is 1 over 2. If I draw that one sort of with the other orientation, so maybe the 60-degree angle is going to come up around here. And so that one should be at a half and root 3 over 2. And then I could just basically make my way around and draw all of these sides here. So all of them with an R of 1. What I'm basically drawing here, if I had a decent scale, which I'm not convinced that I do here because I'm sort of doing this mostly freehand, that would be at 0 and 1. I'd get another one over here. And I'm going to fill in the whole circle doing this in a second. And that would be at 1 and 0. What we've actually got here is, I haven't drawn the triangles because that's going to get a little bit too messy, but I've drawn all of the points that go with, for example, if this is 45 degrees, we'll draw these. And this would be 30 degrees, and this is 0 degrees, 60 degrees, 90 degrees. I'm going to fill in the rest of them. But we should hopefully be seeing if my scale was a little bit nicer, but we sort of have the starts of a circle here because all of these have radius 1. A circle is a collection of points that are the same distance from the middle. We are in fact drawing a circle. And what you will also find is that the sine ratio and the cos ratio are actually given as the coordinates of the points. So in all of these, the x is cos theta, and the y is sine theta. So I'm just going to fill in the rest of those. All right, so I just made the rest of this whole scale. Hopefully you see that circle a little bit better. And then hopefully you'll also believe me if we were to draw these triangles for each one of these angles, because the R value is 1 every single time, what we get as a result of that is that because cos theta is just x over r, cos theta is just x. And because sine theta is just y over r, sine theta is just 1. And so from this picture, what we're going to be able to do is get an idea of what the graph of a sine theta and cos theta function looks like. I could go through and evaluate all of the numbers. If you look at the written notes, there's a table there with them all as decimals. But I'm going to show a little bit of a different method here because I have the luxury of a bit of a video. So yeah, if we start with sine theta, so what we can see happening here is when theta equals 0 degrees, then sine theta is 0, right? It's just the y value of that point, 1 and 0, that goes with the 0 degrees. And then as it goes to 90 degrees, the y values actually start going up to 1. And we can actually see they kind of they go pretty fast initially up to 1, and then it starts to actually slow down at 1, because then as we go to 180 degrees, the y values, as we make our way around this circle to 180 degrees, the y values start going back down to 0. And then as we go to 270 degrees, we're at the bottom half of the circle. So now what's happening is the y values actually keep going down to -1 and then back up to 1. Just going to move this so I can make a little bit more sense of it. And then what would happen then, 360 is basically going to behave the same as 0, so it would keep going. And so what we're getting for the graph of this, if we were to actually try to draw it, is, let's draw this one in, let's say red for sine. So let's say I call this y equals sine theta, my theta axis and my y axis. So we can see is it starts at 0, and then, so I'll try to get that in black. And then our key points that I'm looking at here are going to be 90 degrees, 180 degrees, 270, 360. And so what we can see happening is it goes up and then down to 0 and then down to that should be to -1. That doesn't look very good. So I'm going to fix it down to -1 and then back up to 0. And then what we should see happening is it actually is just going to keep following this pattern again and again and again, because as we cycle through circles, we just repeat the same values. We go through the same circle, and it'll actually go also if we make our way backwards. So this is more or less what the graph of the sine function looks like. If we look at cosine, it's very similar. So cos theta, I'm just going to draw the graph without the descriptors. Cos theta, it has a very, very similar pattern. You'll actually see that it's actually just a shift of the other one. Notice that I am writing a scale for these because I'm not using a traditional scale of just like 1, 2, 3, 4. What comes next? 450, 540. And so with cosine, let's say I do this one in, I don't know, green. Cosine, you can see cosine is now the x as we start at 0, and the x actually starts at 1. And then as we make our way counterclockwise, the x gets closer to 0 at 90 degrees, and then at 180 degrees, it's actually negative because we're on the left side of the graph, and it's referring to x, and then it'll go back up to 0, and then to 360, and then it's actually just going to repeat that same shape again and again and again. So the cosine graph, actually, if you look at it, you can see it's actually just a shift of 90 degrees to the left of the sine graph. So the sine graph, if you start right here at 90 and then end at 450, you have that exact same kind of big dip shape of the cosine graph. They are very, very close related. Yeah, you get what's called a sine wave or a cosine wave. So some of the big features that I want to describe of it. So I'm going to get rid of this whole wacky wheel of numbers here. There's going to be some key features that we'll talk about, and we're going to need these features to do graphing in later sections to make it a little bit more practical. So key features. So both of them have a minimum and maximum value of 1 and negative 1 and 1. So a maximum y value of 1 and a minimum y value of negative 1. So they're trapped. They bounce up and down between positive 1 and negative 1. I didn't actually label this one down here, but yeah, so we're going to get that. Both of them have what we call a period. So a period just means like a shape in a graph that repeats itself. And it shouldn't really matter where you start as long as you're using a consistent distance. So you can see that this shape here, every 360 degrees, we get the exact same shape in actually both of these graphs. We would have the exact same shape. And so we call that a period. And we can't make that, that range any smaller without not getting the same shapes repeating. So both have a period of 360 degrees or 2 pi if you want to use radians. So yeah, so those are like the really, really interesting features. The other thing I'd probably want to focus on is that the starting shape of sine, or if you want to call it the starting period. So what it looks like is this kind of like little jump up followed by a little jump down, and we can identify it by the 5 points. So the 2 endpoints, the midpoint, and then the quarter points. And the starting shape of cosine, unless you want to do a shift, but otherwise it's actually behaves like it looks like a big dip. But again, we can break it into quarters, and it takes 5 points to cap off all of those quarters. So these are going to be some of the key features, and what we're going to talk about next is doing some transformations on these, and hopefully not using transformation methods to do these.